first. Ed leads the research software group in Bear, and he's got a team of 10, is it now? So research software engineers, and he's going to be giving us an introduction to Python, to the toolboxes that you use. And then we've got Warrick up here. Warrick Ball is going to be giving a case study on how he makes use of Python in his area of physics and astronomy. And then I'll sort of wrap up at the end with the sort of talk about the poll results that we got from the first session in January, and our plans for the next session. Okay, so I'll hand over to Ed.
Okay, can you all hear me? Give me a wave or a something. Aslam, can you hear me?
Yes, I can. I would have said so, but I was on mute, unfortunately.
That's fine. Right, find me slides. Okay, so I'm going to talk about Python and its ecosystem. I'm going to use that word a few times, although you kind of can do this entire talk without that word, but it's useful for the last but one slide, which I'll show you when we get there. Who are we? The research software group, so that's the group I lead. We are in advanced research computing in IT services, and we support the computing services of Bear and the software that runs on them. And we provide free advice and support and coaching and coding, working with researchers from all over the university, PhD students through to professors, PVCs. We've worked with most different roles on campus. And we can also join research projects or groups for longer. Funded term contributions, it says there. They range from a few weeks to 3 years at the moment, which is why the team has grown to the size it is, because we keep selling people and having to get more, which is good. A little bit about who I am. So in 1999, I started programming in Python 1.5.2. And I have seen a number of big major Python version upgrades, and they're often quite interesting because you have to do changes to statements to functions or different types of objects or library renames and so on. These days, Python 3, I think, is pretty much here to stay for quite a while. I won't read out everything on all these slides, but I have essentially done lots of Python. And if you want to know more about me, that link at the bottom. This is a talk. I'm assuming that most people in the room are researchers in one form or another. But I hope if you're not a researcher, this will still be an interesting talk if you're interested in using Python while you're coding. This is what I'm going to do in the next 10 or 15 minutes, probably 15 minutes. 3 sections, I will tell you as we go. First one, getting and using Python packages. What version of Python should you be using? Put this slide on because Python 2.7 is end of life. It is not supported. It has security vulnerabilities that are not patched. You shouldn't be using Python 2.7. The general Python community has been saying this for some years, but a lot of researchers still use Python 2.7. Please don't. Please move to Python 3. If you want help, we will help you move to Python 3. Rather surprisingly, also Python 3.6 is no longer supported or getting security updates, and it is the version of Python you get if you install a new machine with CentOS on it, CentOS Stream 8. So just be a bit aware of what version of Python you're using. Most things these days, if you set up a new project, will set up with Python 3.9. Which operating system you're using, it matters, because if you're writing a library that you want to work with other people who might be using other operating systems, you need to know that some of the modules don't exist or don't work the same way for different OSs. Obvious examples are things like the libraries for accessing Windows shell or the ones for accessing Linux password and authentication. WSL, I don't know if you know about WSL, the Windows subsystem for Linux, is something of a game changer, really, for allowing you to do decent kind of console development in Python on a Windows machine. I think Windows have really figured out something clever there. If you've got a Windows machine and haven't tried WSL, it stands for Windows Subsystem for Linux. And you can install it. It's in the sort of standard Windows software center. You can install it and you can just download Ubuntu and run it in your Windows machine. Just double click Ubuntu, you have an Ubuntu prompt. If you get WSL version 2, which won't work on the standard university version of Windows yet, but will do in due course, WSL 2 has integrated graphical applications as well. So you can run a graphical Linux app on your Windows machine. Which Python? This is a question that probably won't be relevant to most people. There are actually two implementations of Python. There is CPython, which is the normal one, which is the sort of reference implementation and the one that everybody uses, apart from the few people who use PyPy, which is a Python implementation of Python. And somewhat ironically, the Python implementation of Python is often significantly faster than the C implementation of Python. It's partly because they've made some different design decisions around things like garbage collection strategies. If you are interested in that, if you think that you might be able to benefit from that, go and have a look at that link, which tells you the differences. But fundamentally, unless you really know you want to use PyPy, just use CPython. Don't be lured in by the community who say PyPy is best. How do you get hold of stuff? If you want to use somebody else's Python package, which is often what you want to do, if you're doing a bit of data analysis, you've got a 20 million line CSV file and you want to analyze it. You want to download things like pandas and NumPy and SciPy. How do you get hold of them? This is my preferred way of doing that kind of thing. You make a virtual environment, which is what that Python -mvenv bit does. It makes a new virtual environment with the name myvenv. You get into it, which is what that second line does, and then you install whatever you want. So pip install NumPy gets the Python numeric library. And you can get SciPy and pandas and PyTorch and all the sort of standard hundreds, thousands of packages that way. There is another way, and this is preferred in some different parts of academia, which is to use Conda instead of pip. You can use pip in Conda as well, which is slightly confusing, but I won't go into that. Conda is a slightly broader concept than pip, because it's not just for Python. But the idea is the same, the paradigm is the same. You make a new environment and you activate it, and then you install stuff in it. So, obvious question next, which one do you use? And the image at the top right hopefully implies that there is no one perfectly right way here. The penultimate big bullet point on there, you need to choose talk to local colleagues or others in your field, is the really important point. If you're working with a supervisor who uses Conda all the time, don't say, I'm never going to use Conda, I don't like it, I'm going to use pip, because you're just going to keep clashing. If you work in a field where everybody publishes their libraries to the Python package index, PyPy, and not to Conda, then insisting that you want to use Conda might not be very helpful. If likewise the other way round, some fields publish all of their stuff to Conda, but not to PyPy, to pip. So you probably want to use Conda in that situation. One thing to note, a little warning, is Conda in particular is recommended against if you're using HPC high performance computers. If performance matters for the things you are installing, the Python packages you're installing, Conda generally will install suboptimal packages. often performance doesn't matter. You've got a laptop, it's got 4 cores. If it takes 30 minutes rather than 20 minutes, well, you'll be making a cup of tea anyway, so it doesn't matter. BEAR, Birmingham Environment for Academic Research, that's the stuff that we do, Advanced Research Computing. The compute environments on there. We will warn you against using either of these approaches on BEAR, because we've got something like 1,200 different applications installed now, and you can see them listed in the BEAR Apps website, which is that link at the top. The reason that we warn you against using either of these things is it's very easy to get into trouble with illegal instruction errors, because if you compile your binary code on one of our new Ice Lake nodes, they're very nice. They've got 72 cores, 76 cores, something like that. They've got half a terabyte of RAM. They're very nice machines. If you then later try and run that one on one of the slightly older machines, say the Haswell or Broadwell nodes, it will almost certainly just explode with illegal instruction errors, and you'll then spend several weeks figuring out what you did wrong. And the answer was, well, not really anything. It's just a quirk of a multi-architecture system. We have a web page which is linked to there, which tells you how to safely install stuff yourself if you need to. But we're always happy to install things for people. Okay, that's getting stuff that you want to use that other people have written. How about writing your own Python code? First thing you need to choose is how you're going to actually write your editor. Are you going to use? Don't use notepad.exe. Ultimately, there are things that editors or IDEs, integrated development environments, things they can do for you that will save you an enormous amount of hassle. Don't write your code in Word. I've seen it. I've seen it quite often. Don't write your code in Word. Write your code in something that understands the language, something that can highlight the syntax, that can highlight if there are problems with the syntax. So if you have a quote where you've opened the quote but you haven't closed it again, all the rest of the file will be purple if you're using my particular version of Vim, and you know there's something wrong with it. Otherwise, you'll get the statements in one color, the strings in another color, the variable names in another color. It's really useful. It saves you time. Integrated development environments do lots more than that. They can do things like autocomplete. So they understand about the libraries you've put import statements for at the top of your file. And you start typing numpy dot, and it starts giving you a list of all the things that it might want you might think you might want to choose. They also do the opposite. If you start typing numpy dot, they give you a warning saying you're using numpy, but you haven't actually imported it. Shall I put an import statement in for you, sir? And you'll go, yes, please. That'll be very helpful. They can do lots more. They can manage virtual environments. They can make test files, run your linting and integrate with version control, loads of stuff. It's a choice, really, of how much you want your IDE to do for you and how much you want to do yourself. If you're like me, and some of the time you know you're going to have to write source code in a text terminal on some remote cluster somewhere, I'd suggest you shouldn't use really all singing, all dancing IDE all the time, because you might actually forget how to write Python. It happens. You log into the remote thing, you open the file, and you go, I can't remember. It always just fills it in for me. But if you can't decide, or if you're new to coding in Python, one of the best IDEs, and the one I used all the way through my PhD, is PyCharm. It's brilliant, and there's a free community version. If you want to pay them money, you can code in other languages and do other things. But if you just want to use Python, the community version's got it all, pretty much. VS Code is also pretty good, and we have that in the Bear portal, which is the web interface to Bluebear's compute systems. If you want to talk to us about that, grab us at the end. Version control. This is where we won't put a show of hands because it never helps. But what I want to say is just use version control for every bit of code you ever write. It really doesn't take very much time to add your code to version control, and you'll very rarely regret adding it. You may well regret not adding it. there are lots of interesting posts online about why should I use version control. I'm not going to go into it, but if you follow that link, there's a nice list and there's a whole bunch of other things. The other thing to say around this is you should always give your code a license. That might not seem obvious. Why do I want to give my code a license? It's only for me. I'm the only one who's ever going to use it. Well, okay, you probably get away with it. If you're ever going to share it with anyone, if you want to make it public, if you don't give it a license and it's on, say, GitHub are very clear. That means nobody else is allowed to download it or use it if you haven't given it a license. People do, of course, and then there's all this legal ambiguity, and we don't like legal ambiguity. I can't even say legal ambiguity. If you put a license on there, there is no legal ambiguity. You are saying, you may use my code. You might say, you may only use it for non-commercial purposes. You might say, you must always attribute to me. You might say that if you make changes to my code, you've got to share those changes. And all of these sort of different approaches, if you go to choosealicense.com, it asks you questions. You go through tick, 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 and it will say, I suggest you use this license. The one I always use for my code is the MIT license, which basically says, do what you like. Because, you know, open research and all that. Okay, when coding in Python, it's good to have fewer bugs. I don't think anyone's going to argue with that. Every substantial piece of software ever written has bugs in it. Not only has had bugs, but has them now. Sometimes you just don't know where they are. All code has bugs. If you came to my coding club talk last month, you'll have seen some of the high-profile research career destroying examples of that. Hopefully none of you will be in that position, but all the code that you've written will have bugs in it. It just does. Some of them might not matter. Some of them are in code paths that are rarely traveled. Flake 8 is a syntax checker, essentially. And it's really valuable if you're writing Python. You run it, and it says stuff like this. That second one, undefined name result, and that could be anything. It could be undefined name badger, you know, anything at all. That one has saved me lots of time, several times in my career, because it finds the thing in the rarely traveled code path where you just never manage to quite update that bit of code to match all of the rest of it. And the variable that you used to define in a global scope that now is defined somewhere down in an if block is no longer there for this rarely traveled bit of code. Flake 8 will find that straight away. It will say, well, there is no thing there in scope called result. And you found a bug straight away. Blank line at end of file is not a bug. Don't know if you know that. That's perfectly reasonable. You might want a blank line at the end of your file. If you're using Flake 8, by default, it will say, I don't like that. You can choose to ignore that error, and you can put that in your Flake 8 config and say, ignore that error, don't care about it. And sometimes you just need to change your coding style to match what Flake 8 wants. That is easier than configuring Flake 8 to match your coding style. And if you match what Flake 8 wants, and you're talking to someone else who codes in a way that matches what Flake 8 wants, you'll be able to read each other's code really easily. Okay, valuable and easy. Those are the things we like. Unit tests, very valuable, still harder to do. Don't avoid them, okay? Someday you're going to have to put the unit tests in. It's way harder to do it later than to do it at the start, but you should still do it. In my PhD, I didn't write unit tests from the start. You know, unit tests anonymous. I'll stand up. Well, I'm not anonymous. I was giving a talk on good Python coding, and I knew I was going to have to write the unit tests in my code before I could stand up and give that talk. Okay, so I did. I didn't get the whole thing covered, but I got quite a lot. And it was hard because sometimes the code I'd written wasn't easy to test. If you set off from the beginning of your code thinking, I want to test this, then you write it in functions, in classes, in files that are more easy to test. You say, okay, well, this is a thing. I can put data into that and get data out. It doesn't interact with any other systems. I can easily write a unit test for that, and that takes 100 lines of my logic and tests it. And then I can write something else on top that uses that, but does more complicated, harder to test stuff without having it all in one function and not being able to test any of it. We can help you write your tests if you want. This one is brilliant. This is probably my favorite thing that people don't ever do. Code review is the code equivalent of document review. That is not a complicated thing to say. If you've ever given anyone else a document to proofread, you will know that in almost all circumstances, they come back and point out something. They might point out something that you've been really stupid and said, and that you've left your recipe for soup in the middle of it because you put it there when you were just writing the document and didn't know what you were going to put in that section. Or they might point out just like spelling errors, typos, ways you could improve it. It's all the same with code review. The key things I want to say about code review are what's in bold on there. If you are going to ask someone else to review your code, then trust them, be brave, be really clear about what you want them to do. And if you're reviewing somebody else's code, be nice about it, because someday you're going to ask the other person to review your code. And actually, sometimes it's easy on a kind of grumpy Thursday afternoon to be reviewing someone's code and you say, oh, you should not do it like this. Blah, 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 blah. Say it nicely. If at all possible, instead of making a comment about how you think it should be done, put a suggestion in GitLab or GitHub. That's a way that they have got, is a really useful feature, where instead of a comment on the code, you press a little box and you can edit the code, press send, and then the person who's looking at it goes, I like what you've done there, and they can just go apply, like suggested edits in Word. It's exactly the same concept. And I saw a really interesting tweet by someone saying, if it's not worth your time to do it as a suggestion, it's not worth the other person's time to understand your comment and make the change themselves. Which I think is probably true if you're in like a commercial team where everybody is invested in the project. If you're asking your co-PhD student over here, who you know has got hardly any time, that may not be as true. I've got to speed up, I think. Publishing your own Python code. Why do it? You will have your own reasons of wanting to publish it. You might not want to publish your code. If you make your code open and publicly accessible, you may be in the lucky position that other people will use it and find problems with it and make improvements to it. And it might become the next big thing. Might. I guess it probably won't, but it could do. There are tools that make it easier. You can attach GitHub and Zenodo together, which means every time you make a release in GitHub, Zenodo gets it downloads a copy of all of the files, zips it up, puts a DOI on it, and links it back to your GitHub. That thing at the top right is a Zenodo record for some of my software. And you can install directly from GitHub as well. If you put it on GitHub, other people can just get your code by doing pip install that. There are standard places that you get your code from. Back to the beginning of my talk, I was talking about installing with pip or installing with Conda. You may well want to put your code in one of those two places. If you do it well, which is what the last comment says. Final point, the reason I was saying ecosystem earlier, it actually really helps in the Google searches. So if you are a mech-eng student or a bioinformatics professor or whatever, if you Google Pico ecosystem for my field, someone somewhere has done a YouTube video and written a paper and done a blog post about what they suggest you do if you were using Python in that domain. And I cannot speak for them all, obviously, but the ones I've seen are really helpful. And they will say things like, everyone in the field uses Conda. You think that's very helpful. I will use Conda. And it's alphabetical, as you can see. I put zoology, but if you put zoology ecosystem, you get into all kinds of trouble. So I didn't put that as the example. Okay, questions. I guess we've got about 2 minutes then to give Warwick his proper due time. But we started 5 minutes late, so I think I'm feeling all right about it. Debbie, are you going to coordinate questions? Or are you just coordinating online questions? All right, in that case, there was a hand in the room. So, Adrian. Yeah, so you can have 10,000 source files. You go to the top level and just run discover, and it will run all of the tests and report out amalgamated results for them. Oh, Dietmar's raised his hand. Go for it, Dietmar. Unmute.
Yes, will do. Thanks. I've come across style guides recently. Is that something you would recommend? Is there one for Python that's generally agreed?
Yes. So generally for Python, it's called PEP8, which is the Python Enhancement Proposal number 8, which is implemented in Flake8, which is the piece of software I was showing.
Right,
so,
I see.
There is also other stuff around PEP8. There's a really useful thing. There's a tool you can install called Auto PEP8, where if you have Python code and you run Auto PEP8, it does everything it can to convert your code into PEP8 compliant style, which is really helpful. So that will save you hours of indenting and adding new lines and things. So yeah, Flake8, PEP8, that's what I would suggest.
Yeah, okay. Do you want to tell the audience a bit about it about style guides in general? I don't know whether that's the right place.
So almost every language will have one or more accepted de facto kind of guides on how you should write your code. So how you indent, how you format, what you put as your, how you use case for your function names, variable names, class names, etc. Finding the accepted style guide, possibly in your field, but probably just for the language you're using, is very valuable. And find the right one if you can, choose one, stick to it until you find a better one. And don't get lured into thinking this is just a quick script, I don't care about it, I'll just hack it together any old how, because that's a good way to introduce extra bugs that things like Flake8 won't be able to show you because it can't understand your style. Probably one more question if there is one. Warwick, is this, can I do my talk now?
No, just to follow up with that. I'd say also use an editor.
Yes, yeah, thank you for that. So for people who might not have heard, Warwick's point is use an editor that enforces your style. So things like PyCharm, you can just tell it, I want my code to be Flake8 compliant, PEP8 compliant, and it will give you red wiggly lines whenever you're doing bad things. And if you click on it, it'll take, it'll fix it for you.
I see, that's interesting. Yes, thanks.
Go on, read it out. So is there a good source of example code that a new coder can go to, someone without a coding background? Is that it? Several answers to that. The Python library reference is the place that documents all of the standard Python library modules. And each of them has code snippets of how to use it. But then there are things like, if you go to the TensorFlow website, they have loads of examples of how to use TensorFlow if that's what you want to use, or NumPy or whatever. I would suggest probably Google is the answer. Whether or not it's going to be good code, well, it probably will be if it's associated with one of the big standard packages or with python.org itself. And I would just say the one final thing that I implied earlier, if you want any help with your coding in general or with Python coding, then do get in touch with us, bear-software@contacts.bham.ac.uk, and we will help you. Right, I better hand over the floor, I think.
Everyone. So my name's Warrick Ball. I'm a postdoc in the School of Physics and Astronomy, in particular in the group called Sun, Stars, and Exoplanets, where what I do as a scientist is I make models of stars, somewhat slightly approximated, and I compare those models to observations. In particular, I'll have colleagues and collaborators who measure the frequencies at which these stars might be vibrating, and I try to make a model that would vibrate at the same frequency as those observed stars. And that tells us maybe something fundamental about the star, like how massive it is, or for me, more interestingly, is whether we actually understand what's happening inside. How good are those approximations and which do better at reproducing the data? So I certainly think of myself as an advocate of the open source movement, of hacking culture in general. So I'm glad to see this getting started again. I'm very glad that you've given me the opportunity to speak, and I'm always happy to talk about stuff like this. And I've just put there that you can usually find me on Teams through the university system, on the Birmingham RSC Slack, or just by email. To make a case study of myself briefly, there's a project I want to spend most of my time talking about, given that I wasn't entirely sure what I was meant to be talking about. But for myself as a case study, this is actually a reasonable cross-section of what I do. This is just my GitHub user page. And curiously, those 6 most popular repositories are firstly a set of Python scripts that I use to generate the plots that I use both in outreach and also in my teaching. So if a student comes along and wants to, play with the parameters or something, in theory they can check out the repo and play around with it. I have released a Python package, you can pip install it, which allows you to work with some of the special data formats that we use in my field. In particular, there's some fixed format files that we pass around, and moving things between them got annoying. I started writing functions, eventually turned that into a library, eventually it went onto pip, became unit tested. And in fact, the history of that repo is probably a chart of me becoming a more and more open coder. One of them is the scripts to recreate the data from a paper. So the data itself is in a big Zenodo repository somewhere. But if a scientist then goes along and says, I want to see exactly how Warrick calculated this bit, they can go and have a look. One of these is also a Fortran package, because I spend a lot of my time writing in Fortran. And if you think Fortran is an old dead language, I beg to differ, and will happily tell you why that's not the case. And then the last one's a curious one to pop up there, because I'm guilty of what people sometimes call drive-by contributions. So I watch out for new open source packages in the field. I see a new interesting one. I'm like, oh, yes, I'll try to download and run that one. And I try, and something goes wrong. And then I'll look into why that thing went wrong. And maybe I'll open an issue, or in that case, I'll actually make a pull request and say, hey, I think I've worked out why my thing didn't work, and you can have it back, which I think is one of the great things about open source. When you have these expert users who come along and actually can just start changing things because they are licensed to do so. I'm also a core contributor to 2 very big Fortran programs. So these are the main ones I use for the actual number crunching in my field. So the first of them to compute the models of the stars, the second of them to compute the frequencies at which those models would vibrate. And I bring these up because these programs are just one in each case among many that have existed in the field, in some case for decades, going back to Fortran 66 and Fortran 4. But these are the only ones that are truly open source. And they have quickly come to dominate their fields, I think largely because of their open sourciness. So that is, I think, a good demonstration of how valuable this can be in the field, especially for teaching, incidentally. If you have an open source program that's well supported and students can install, you can get going, showing them real research results quite quickly. So the real case study I want to talk about, which I said I would talk about, is recent work I've done with a colleague on trying to make a program called AIMS. That stands for Astroseismic Inference on a Massive Scale, but that doesn't matter. We just call it AIMS. Trying to make it more maintainable. I don't know, there's no particular lesson I want you to take from this or intend for you to take. I just hope that there's something you recognize as something you can relate to, something you might learn, or something you can even teach me. So to understand this, I first need to talk a bit about what it is that AIMS does. So the usual situation we have is that there are things about stars we can measure. So for example, how bright they are, how hot they are, frequencies at which they vibrate. But those are not always the things that we want to know. We want to know things like, how old are they? How massive are they? How big are they? And the way we make that connection is with these models and these vibration codes that I've just mentioned. So you'll go to your computer, you will run Mesa and Jaya on it, and given some of those things we want to know, which are fundamental inputs, things like how massive the star is, it will then predict things like how bright is the star, how hot is it, And also the other stuff which may sometimes be measured but often isn't, the size of the star, its radius being a good example. AIMS does that backwards. So AIMS is the program where, given a lot of information from the simulation programs and given some observations of what a distant star is doing, it will then use that to infer how old is that star, how massive is it, how large is it. And AIMS ended up on our desks because the European Space Agency is going to launch a satellite called Plato. And Plato is going to observe stars and how they vibrate. And parts of AIMS, or maybe even the whole package, might become part of the pipeline that will steadily take you from, photons hitting the detectors and, causing electrons to jump out of potential wells, to being analyzed into catalogs of masses and radii and ages of all these stars that will lead to amazing publications from everyone, grants and permanent jobs all around. This part of the project is funded here in Birmingham. And AIMS was originally developed along these lines. So it was started by a postdoc who's now moved elsewhere, a lot of work by a PhD student who has since graduated. But eventually this landed on the desk of myself and my colleague, Steve Hale. And we decided, well, if we are going to have to maintain AIMS, and it's a perfectly good and scientifically useful code, there are many users out there already, however many published results. If we're going to maintain AIMS, we want AIMS to be more maintainable. And in starting to try and fix some of the things that we think are, well, wrong is probably too strong, but certainly could be done better from a software perspective, we would start changing things. So the first thing is that if you're going to start breaking things, you want to know very quickly when they are broken. And so we set about writing unit tests. So Ed already mentioned these, and I will just digress from it because learning about unit tests and starting to write unit tests was probably one of the best things I ever started doing. One of those things where I immediately regretted that I hadn't been doing it much earlier in my career. Using Git is the other one. It doesn't just make a particular project more robust, okay? It changed the way I write code so that you sit down and think, what here are the testable units? What are the bits that I can lay down and say, right, this bit now works as I expect it to and will continue to do so. And if it stops doing that, I will know. And I think that's a huge thing. But it's also, as mentioned, kind of difficult to do in hindsight. But we had a good go. So Steve did the often underappreciated and under-rewarded infrastructure work of setting up a new GitLab repo, replaying the existing versions into the version control so that they would be tracked and tagged properly, and then setting up the continuous testing infrastructure and scribbling in a few tests. And then I set about trying to improve the coverage, which we eventually got to about 85%, which may or may not be a useful figure because some of those are just tests that execute lines of code and hardly do much to check whether or not they do anything useful. So like many metrics, commit histories are another one. How useful they are is sometimes questionable. But so we wrote some unit tests. And along the way, I learned a lot about how AIMS actually does things. So we cleaned up some little things. And I'll give a few examples of these little things that we tidied up. The first is some of the error handling in the program. So AIMS is currently written as was originally written as a large monolithic script. So you would check it out and you would say, run AIMS on my observations. And if something went wrong, it would quit. A better way of doing this, in a strict sense, is to instead actually raise errors in some of the functions in the main script, because that gives the caller an opportunity to respond. So you said, I've tried to perform this operation, something has gone wrong, and the caller might say, okay, I know how to deal with that, that's fine. And if it doesn't get handled, then it's going to crash the program anyway. So there's no change there. So that was the first thing we set about doing. There are also some curious spins on this. So there were a few blocks where it would try an operation, and if the operation returns an error, it would tell the script to quit, which is unnecessary because like I said, if the exception goes unhandled, I will occasionally use the Java-esque term caught because that's where I originally learned it. If the error is not caught, the program's going to crash. So we don't need the handling logic. The second little thing that we changed is some of the file handling. You may be used to opening the file object, you interact with the file object, you close the file object. Especially in interactive work, that's a perfectly reasonable way of going about things. But as far as I know anyway, a more idiomatic and kind of Pythonic way of doing things is using these things called context managers. So what you have is this very similar looking line, the with open file name, blah. You do some stuff in there, And then with Python's indentation rules, when you leave that block, the file is then closed. There are various benefits, some of which are beyond me. One of them, as far as I know, is that the error handling is better, so that if something happens, if something goes wrong while the context is open, the file will still be wrapped up, will still be closed properly, and that sort of thing. So that was another little thing that we changed. But in cleaning up the little things, we started running into some big things. So some kind of the big architectural decisions which were starting to get in the way of incrementally getting AIMS from where it was to where we wanted it to be. So the first big problem is how options get communicated. In this process of matching the simulation data to some observations, there are a lot of choices you can make. There are things about how the simulation data is structured. There's things about exactly which combination of observations you want to compare. And because AIMS runs a Monte Carlo Markov chain, so MCMC sampler, there are choices about how many samplers, how long will they run for, that kind of thing. And all of these options, we're getting bundled up into a single configuration file, which is itself a Python script. There are kind of like security reasons why this is not a great idea, but just from our own practical point of view, this makes things difficult to test because you keep having to go in and like change the configuration options in that config namespace. And similarly, to work with things interactively, you keep passing options through this other place. And although you can work around these things, it's not great. And it was certainly an obstruction to turning AIMS into something that would be an installable package. This business of not being able to easily work with AIMS installed somewhere else. The second smaller but still quite big problem is something that came from feedback from the users. The simulation data you will prepare in some format. Your simulation code spit out some plain text files, and then AIMS will bundle that up into some rapidly accessible binary format that it can interpolate things and do other things. But that definition was overly strict and kind of incomplete. So there's metadata, other information about the simulation results that you want to pass around as well, but they were being passed around separately. And that's a nuisance because you're quite prone to losing them then. If you've got data in a structure, you want all the data that you need to be in that one structure, and then you just pass that one structure around. And so these two meant that there were quite substantial things you're going to change. So we needed to change what simulation data was going to look like. We need to change how the user is going to be interacting and passing options. So I decided that the best way to proceed was something like this, from scratch. With two remarks I'd make about this. The first is that, okay, it's not actually from scratch because I've worked with AIMS and I've seen how AIMS worked. And a lot of what I rewrote re-implements what it does. I don't think I ultimately actually copied any code. So I did rewrite everything, but it's mimics very closely and was closely tested against the existing results. And secondly, remember that this is mostly possible because AIMS is open source. AIMS is licensed under the GNU General Public License, which is one of what's known as copyleft licenses. So if someone gives you GPL license code, you can create derivatives as long as you also license them under the GPL, which I'm very happy with because I think GPL is a very good choice for substantial research codes, and all those big Fortran programs I talked about are all GPL licensed. So with that in hand, I could start rewriting AIMS. And if I'm going to rewrite AIMS, I thought to myself, not in the sense that I sat down and just thought, let's now think about this perfectly, but rather as you're working through, you're building up this picture of what it is that you really think the program ought to look like. And the questions I was thinking about are stuff like this, like what does AIMS actually do? What steps is this monolithic script performing in the journey from observations and simulations to inferences about how old a given star is? And a spin on that is to think of which parts could I remove? And if I left the interfaces looking roughly the same, the rest of the code probably wouldn't care, which in a sense is getting back to what are the units here? And I also like to think about, because I've gotten used to in Python manipulating things like you can abuse what the indexing notation does for objects that you define. So you can define some of the get item functions and things. So I started thinking also, for someone who works in my field, if they sit down and they get data in this format, what are the things that they expect to be able to do? Okay, and how shall I go about implementing them? So what does AIMS do? Okay, it defines a likelihood given some observations of a model. So I should be able to say, I've got a likelihood, I want to evaluate my model, and it will spit out a number. I don't know, the model is good, it's 10. The model's bad, it's 20,000, great. Ames compiles the simulation data into this grid that allows interpolation and faster access because it's a binary format. And Ames then runs an MCMC sampler on this likelihood. It so happens that Ames uses a deprecated MCMC sampler. So one of the first decisions I made was that I'm not going to worry about this because there are so many different samplers out there. There are so many different optimization methods. I leave it to you to choose the one that you're going to use. And I'm going to worry about the other things that are really what Ames does. The data has a natural structure to it already that should be respected. Ames already does this, but it's worth making sure that it's preserved and the way we expect to interact with it is also preserved. So the way the simulation code works is that if you start with a star that is, say, quite cold and relatively faint, and then the simulation code will take one step forward in time, which will be, in my case, a few tens or hundreds of millions of years, and you get a new model. And then you'll take another time step. And you'll carry on doing that until you get to some stopping condition, which will be whatever it is in this case, somewhere where this star happens to be cold and bright. That sequence of models we refer to as a track, an evolutionary track. So it's got a fixed set of initial parameters, and the age is changing. So that's one thing we need to respect. Our tracks are sequences of models, but I don't compare one track to the data. I compare a whole lot of these different initial parameters, and that gives me a grid of tracks. And that is how people in the field talk about it. They say, I have a grid of tracks, and my tracks contain models. And that's something that should be respected. And to take that a step further, I implemented things like, if I have a track, the track has a length, right? There's a number of models in it. I should be able to slice a track and choose certain subsets of models from that track. And so too with the grid, et cetera, et cetera. No, those are all things that can then be implemented and tested. I already mentioned the way the likelihood function should probably look would be in a kind of quasi, somewhere between pseudocode and Python, something like, okay, I'm going to get a likelihood. I'm going to create a likelihood object, which will be initialized somehow from the observations. And then I want to be able to evaluate my likelihood given a certain model in the sense justified. And like I say, that will spit out a number. And so what that means in terms of code is that you want some kind of initialization which will take in your observations. This isn't exactly how it turned out in practice, but this is the thinking that got me there. And then to evaluate the likelihood, we want to define a call, which in this case gives you something like a chi-squared, but perhaps it will be something else or evaluated differently. So this is just the procedure of how I'm going from what I'm expecting users to want to do to how it is that that kind of thing will be implemented. Finally, regarding the data format, this is what it used to look like. So there is some cryptic metadata. It's actually just the prefix and postfix for the file names, which are the first column, and then some other stuff whose meaning I know, but you have no idea. It is documented, to be fair, but has to occur in a certain order. And any additional columns is extra information that has to be passed around in the enormous configuration file, and like I said, is prone to getting lost, and then the program stops working. So the new data file is only a simple expansion on this, where I allow an arbitrary, what's called YAML. So I think it's yet another markup language is the acronym, which is fairly standard across a bunch of things. I think it turns up in Python package configuration files these days as well, and allows you to basically define something that looks a bit like a dictionary. So these will be passed into Python in quite natural form. And then the other thing is that there's a second block where we include the column names. And I use NumPy's gen_from_text function to read data with column names all the time. It returns what's called a structured array rather than just a plain old array. And that allows you to access the data by column name, which is often more meaningful. And that means the order doesn't matter. The contents actually don't matter that much either. You can tack on whatever other garbage you want further to the right. And Ames will still get to what it needs to. And you don't have to pass extra information about this stuff. And just as a working example, this is something I am genuinely working on at the moment. There's a lot of metadata we might want to pass along. So this includes things like, in the interest of reproducibility, which program I use to generate the data and the version numbers, as well as simple timestamps, project, and then physical constants and all sorts. And then you see the block at the end. So I started with the snippet of the documentation from the old Ames. This is the documentation, a snippet of documentation from the new Ames, where, for example, I've defined this track object you see here. The stats module is the one that has the likelihood, and you can see the grid, the track, and the model as I defined. I also ended up creating a little test data creator because compiling actual simulation data is itself quite complicated. And therefore, creating what you need for unit tests becomes quite a nuisance. So there's a module there that generates something that is not scientifically useful, but has the correct structure and mimics all the important properties we need. And then here the documentation starts off by explaining to you how it is that you can manipulate a track in a similar way to a list, really, including things like appending and extending with other models or tracks. And that's where I'll stop. Yeah, that's right. Shall I say, go ahead. As far as I know, YAML is quite easy to process, and I jumped at it for its simplicity. Fair question. So yeah, the question is why YAML rather than something else like XML? I must say, I didn't give it that much thought. I did not survey to see what everyone else uses, but it's one I'd come across. I've seen people talk about in a few of the projects I do work in, and is simple enough that, I mean, for me, one of the most important properties is that the plain text representation is easily human readable. So someone simply loads up this file, and even another astronomer who doesn't work in my niche would probably have a good idea of what's going on just from those contents alone.
I've got one question.
Yeah, sure.
So you mentioned you put all scripts available.
Yes.
Yeah. Have you ever had any
No, I'm trying to think about that across all the projects I've led. So I've had some pull requests for stuff like one of the data formats we use, for example, is not very well defined. And so someone had a code that produced something that, strictly speaking, still satisfied the requirements, but wasn't one I'd ever come across before. And so I then had to then go in and check that that was that would still work in a reasonable fashion. Then looking forward to, okay, what other weird variations might people give me? But no, I haven't had that yet. Yes. Yeah, I think one of them, yeah, that's that same package. I was randomly looking at some quite fascinating work, another story that another group's doing. And when I was looking through their Python scripts for how they'd set stuff up, I noticed that they were actually using that package of mine. So that was quite nice because it's an individual who I've never interacted with. I've never seen them at a conference. It's probably at least 2 degrees of scientific separation who somehow came across it, which is quite nice.
Any other questions?
The idea that you get tested in little abstract. I mean, I don't know if it's more an question or a Warrick.
Well, I can try my best.
For example, are you coding your expectations about it, and then comparing that to code?
Yeah. So the question is, what is a unit test? Are you encoding what you expect the function call to return? And the answer is yes. So the unit tests are. So I've written the code. Ideally, you'll do this so that it has certain functions which perform compact, well-defined operations in some sense. So it might read a file. It might, in my case, it might take a luminosity and a radius and create an effective temperature, surface temperature for the star. That's something you can do. And so what the tests do is they call that function with those known inputs and compare it to the expected output. However many variations of those you can cover. An important addition I would make is that one should also test failure. So it's also good to call your function with something that shouldn't work and make sure that the function does not work in a useful way. Because I've certainly had experience where you give code garbage and it's just quite happy to carry on computing with the garbage, producing nothing more than more garbage along the way. And then, you kill your job after 6 hours on Blue Bear and look at all the nans that have come out. So yeah, test failure as well, but that's exactly the idea. There's also the separate idea of, I think, integration testing is where you try to test the program in some sense as a whole.
Well, we've been a little bit over. Many thanks to Ed and Warwick today. I just wanted to say after Ed's talk, you know, if you are interested in Python, you're sort of starting out, we've got the Python Carpentries course, which is a 2 half-day workshop. Places available on that, and that's on the 15th and 16th of March. And you can book a place through the Bear training link on there. I just wanted to very briefly cover what we found out from the last January session. We did a sort of poll on what people thought about moving forward with the coding club. And the aims, a lot of people wanted to learn something new, which is great. Around topics, R is very popular. Also reviewing code, and that's come up quite a bit in the talks today as well. So I'm hoping we can cover that in future sessions. If to keep in the loop with the coding club, we have got a mailing list which you can join. Details on there on how to do that. And we've just started a Teams channel as well, because we thought it's easier to sort of discuss things if you've got a problem on there. We've also got RSC Slack, which Warwick did mention. If you're interested in that, just get in touch with Debbie or myself at Steph Thompson, and we can give you the details on how to join up to that. And there is a Canvas course where we'll be putting all the slides from today, and the recording from the session will go onto that Canvas course, and that's the link to enroll for it. And yeah, finally, the coding club needs you really. We need researchers. We're from the Bear team. We're happy to coordinate it, and Ed's provided some the talks, but we really want to have help from researchers so that you can direct where the club goes, and help us find speakers, and chair sessions potentially. But yeah, we will fully support you in that. So if you're interested, just get in touch. And the key thing really as well is the next session we haven't got speakers for at the moment. As you see from the poll results, everyone's really interested in an R session. So we're really looking for a speaker for to give us like an introductory session like Ed gave for Python, but also to give a case study like Warwick did on Python on how you use R in your research. So if you're interested, just get if you're in the room, come see us, or send a message on the chat, or you can email us at bearinfo. Debbie can put that link in the chat. Thanks to everyone for joining us. Hope to see you at the next session.